Just a quick comment on the previous clip, just to understand this intuitively a little better. If 98 joules of work goes into the system from non-conservative forces, and the kinetic energy of the system goes down by the 12 joules done by the net force on the system, by the net force exerted by the system, okay, then the 98 joules that goes in here is going to tend to raise the mechanical energy, which means that the potential energy would have to go up. And if the kinetic energy goes down by 12 joules, then that's going to require, or that could, let me say it clearly, if the kinetic energy goes down by 12 joules, that would correspond, if the change came from potential energy, that would correspond to an increase of 12 joules in the potential energy. So potential energy, or kinetic energy, goes down by 12 joules to increase the potential energy, so that the 98 joules tends to increase the potential energy. The 12 joules of kinetic energy loss tend to increase the potential energy, so that the potential energy change is 110 joules. That's a little bit tricky to understand, actually, so it's a little bit tricky to say. But it's well worth thinking through. Now, we want to go to this example. We have a 109 kilogram object. Let's say it's attached to a spring, and the spring is right here in what we're going to call its equilibrium configuration or position. We raise the object 1.2 meters, which stretches the spring out 1.2 meters, and at this point we have a 780 Newton tension in the spring. Then we release the system. We just let the thing go. And what happens? The potential energy due to gravity decreases, the potential energy due to the spring decreases, and the kinetic energy of the object increases. So we want to know what the kinetic energy is here and what the velocity is here. Intuitively, we know that we have to do something to raise the system, so that there's going to be work done by some external force to get the system from here to here. But as we fall from here to here, we're falling in response to conservative forces of gravity and spring energy, or spring forces. Okay, so let's see. After release, what happens? The net force on the system does a positive amount of work, because the net force on the system is down and the system is moving down. The motion and the force are in the same direction. Therefore, the work done by the system has to be negative, since the work done by the system is negative of the work done on the system, and it follows that the kinetic energy change will be positive. And that's simply because if the work done by the system is negative, then the kinetic energy change is positive. We can do it from this equation, or just from our knowledge that the change in kinetic energy is equal to the work done on the system by the net force. Okay, in any case, the work done by the system is the negative of the average force exerted by the spring times the displacement. Now, the F spring with a bar over it, the bar tells us average. F spring is the force exerted by the spring on the system. The force exerted by the system on the spring is the negative of that by Newton's third law, again, equal and opposite reactions, so forth. Okay? And then it's going to be minus the force of gravity times delta S. And this is negative again for the same reason. The force of gravity is a force exerted on the system by gravity. Negative force of gravity is a force exerted by the system against gravity. Make a side note. We could find the force exerted by the spring, and there are cases where we might need to do this. And find the formula, since the force of the spring is a negative linear force depending on its displacement, where now y is going to be the displacement from equilibrium. We see then that the force of the spring is negative 780 newtons, 780 newtons down, when the displacement is 1.2 meters up. Solving for K, we get K is 650 newtons per meter. So we could say that the force of the spring is negative 650 newtons per meter times the displacement of the spring. Okay, we don't really need that to solve this problem, but I thought it would be good to remind you of how springs behave and to put you in the context of the spring here. Okay. Now we say that the force in the spring is linear. I mean, this is a linear relationship, so that the average force exerted by the spring is the average of the forces at the 2 points between which we're analyzing the system. At this point where the force is 780 newtons, at this point where we're in equilibrium and the tension is 0, the average of those two forces is negative 780 newtons plus 0 over 2, or negative 390 newtons. So the force exerted by gravity, well, okay, this is the average force exerted by the spring. That's just going to go here. Now the force exerted by gravity will be the 109 newtons times the negative 9.8 meters per second squared, or negative 1,070 newtons. Now the work done by the system will then be the negative of the average force exerted by the spring on the system, which is this, times the displacement, and then minus the force exerted by gravity on the system, which is the force exerted by the system against gravity, times the negative 1.2 meters. In any case, we see that the system does negative 1,750 joules of work. The spring and gravity do 1,750 joules of work as the system moves downward. The system does the negative of this. The forces exerted by the system, again, are equal and opposite to the forces exerted on the system. So the work done by the system plus a change in kinetic energy is 0. Since the work done by is negative 1,750 joules, the change in kinetic energy is the negative of the work done by, which is plus 1,750 joules. Now at this point we could go on to find the velocity of the system at equilibrium, because after release the change in kinetic energy is plus 1,750 joules. Just before release the kinetic energy was 0, so after the return to equilibrium the kinetic energy had better be 1,750 joules. It starts at 0 and changes by 1,750, it ends up at 1,750. And that's equal to the 1/2 mv squared. We solve this for v, we get square root of 2ke over m, and then we plug the 1,750 joules of kinetic energy and the 109 kilogram mass into the system, and we get approximately 5.7 meters per second. Now let's think about what happened before release as the object was raised. The work done against conservative forces was positive. Since as we raised the object up, the motion is in the upward direction, and the force exerted by the system has to be in the upward direction. So the work done against conservative forces has to be positive. During this process then, the work done by conservative forces is plus 1,750 joules, and we get that using the same forces that we had before. There's no kinetic energy change, so the work done by the system has to be 0. There's no work dissipated, no energy dissipated. That's an assumption of the problem. So that the work done by the system, which is the work done by the work done against the conservative forces, plus the work done against non-conservative forces, which has to equal 0. Since there's no kinetic energy change, that has to equal 0. This implies that the work done by or against non-conservative forces is negative 1,750 joules. Now what's all that mean? Remember, the work done by or against non-conservative forces is the dissipated work, which we assume is 0, plus the work done by against the external force, so that we see that the work done against the external force is negative 1,750 joules, which means that the external force must have done 1,750 joules of work on the system. All that means is somebody had to come along and raise the system by applying some force external to the system. Something had to lift the weight. And that's our interpretation of this. We can ask one more question about this system. If 1600 joules was dissipated after the system was released, say with the system underwater, so that the friction with the water, turbulence and so forth, dissipates 600 joules of energy, then after the release, the work done by the system has to equal the work done against conservative forces plus the work done against non-conservative forces. Let's say the water resistance. So the work done against conservative forces is negative 1750 joules, which means that conservative forces do plus 1750 joules on the system. Gravity and the spring do that much work on the system. So the work done by the system against conservative forces is the negative of that, plus the work done against non-conservative forces, which is positive. We always do positive work against dissipative forces. Okay, and we assume that all the non-conservative forces here are the dissipative forces, the 600 joules. And that gives us a negative 1150 joules, so the kinetic energy change is just 1150 joules, and we calculate the velocity the same as we did before.